This whale shark is sinking with its mouth open, feeding as gravity carries it down. Scientists had inferred deep feeding before, but this camera finally showed the behavior from the shark's own back. That matters because the largest fish on Earth has a problem that sounds almost impossible. Its body can reach 18 meters, yet much of its food is tiny enough to vanish in open water. And the tropical ocean where it lives is not a limitless soup of plankton. Food appears in patches, separated by water that can look almost empty. The familiar answer was simple: whale sharks cruise near the surface with enormous mouths open. But that familiar image came from the easiest part of their world for humans to watch. Boats, aircraft, and snorkelers could follow only until the shark chose to dive. Then the observation ended while the shark's day continued below them. So, researchers attached cameras and let the animals carry human vision into that missing ocean. What came back was not one spectacular feast, but a completely different picture of how a giant finds enough food. Filter feeding works only when the energy gained from prey exceeds the cost of moving water through the mouth. For a whale shark, opening wide also creates drag, so feeding is never literally free. Dense krill swarms can justify fast, active feeding, but those swarms are temporary. Between them, the shark still has kilometers of comparatively thin water to cross. Earlier tags had already suggested that whale sharks probably forage at depth for substantial portions of the day, but movement data alone could not tell researchers exactly what the animal was doing. A descent could be travel, thermoregulation, gliding, searching, or feeding. The shape of a dive was a clue, not a view. Surface footage also favored the most dramatic behavior, a huge mouth chasing visible concentrations of prey. That made the ocean's quiet, continuous feeding easy to miss. At Ningaloo Reef, the team deployed camera packages on 10 whale sharks during field seasons in 2017 and 2018. The package clamped temporarily to the leading edge of the dorsal fin. It recorded high-resolution movement data and video of the shark's front half and forward view. A timed link released the package after roughly 1 to 2 days. The floating tag then reported its position so the team could recover the footage. Technical problems mattered, some tags dislodged, and debris obscured some lenses. The final analysis used 45 video intervals from 5 sharks totaling 22 hours and 27 minutes. That is the honest denominator, 10 deployments, but usable video from 5 animals. The camera sat behind the head, so it could not directly film the mouth opening below the snout. Researchers instead watched the gill slits and arches for signs of water flowing through an open mouth. That is useful evidence of feeding-related flow, but the paper explicitly treats it as a proxy. The researchers combined the video with 106 papers to build a catalog of 36 whale shark behaviors. 12 involved feeding, and 6 feeding behaviors were novel descriptions from the animal-born cameras. First was gliding slow feeding. The shark sinks with open gills, while gravity supplies much of the downward movement. In the longest recorded example, that feeding glide continued from about 5 meters to almost 65 meters deep. Dive feeding looked more forceful, with the shark actively swimming down while the gills stayed open. Ascent slow feeding reversed the direction, continuing through long rises toward the surface. Water column slow feeding happened where neither the surface nor the seabed was visible. Benthic slow feeding carried the open-gilled shark just above the bottom, and surface undulation slow feeding paired open gills with a persistent rocking motion in the upper meter. The function of that rocking remains uncertain. Feeding is a hypothesis, not the only possible explanation. Together, the behaviors turn a flat surface image into a 3-dimensional feeding toolkit. The biggest reveal is not that whale sharks can feed dramatically. It is that slow feeding behaviors were the most frequent category in the camera footage. Surface slow feeding ranked first, with water column slow feeding close behind. Gliding slow feeding appeared far more often than ordinary closed-mouth gliding. The researchers proposed that slow behaviors may supplement food intake where prey density is low. Then, when a richer patch appears, the shark can switch to faster active feeding. Think of it less as waiting for dinner and more as continuously sampling the ocean between meals. The animal also has 2 ways to move prey-filled water: forward ram filtration and muscular suction. Different behaviors use one mode or alternate between both. Its mouth opening can vary rather than operating as a simple open or closed switch. That flexibility lets the shark scale effort to the feeding opportunity in front of it. A tropical ocean can be productive in brief pulses without being rich everywhere. Fish spawning events, krill swarms, and layers of zooplankton appear at different times and depths. A predator committed to one feeding style would miss many of those opportunities. The whale shark can move between slow, active, and stationary categories using ram filtration, suction, or both. That does not prove each switch is a conscious decision. It describes the behavioral repertoire shaped by movement, anatomy, prey, and conditions. In comparable camera work, basking sharks showed a much narrower visible feeding repertoire. But the authors caution that location and prey differences may explain part of that contrast. The defensible conclusion is narrower and more interesting. Whale sharks possess an unusually flexible feeding toolkit. That flexibility may help a gigantic filter feeder persist where food is scattered and temporary. The camera footage followed 5 usable sharks from 1 juvenile coastal aggregation at Ningaloo Reef. The deepest behavior in the analysis occurred at 68.8 meters. The videos could not resolve individual prey items, and gill movement was not uniquely diagnostic of feeding. So this study did not reveal every feeding decision made by every whale shark. What it does reveal is a set of behaviors that surface observation had largely hidden, and the missing water below this study is enormous. Whale sharks have been recorded diving beyond 1 kilometer into the open ocean. There, the prey fields, darkness, temperature, and purpose of a dive may be completely different. If 6 feeding behaviors appeared in this shallow coastal window, what remains unseen in the deep one? The largest fish on Earth was never simply waiting at the surface. It was speeding through an ocean we had barely learned how to follow. What animal deserves a body cam next?